Have you ever wondered what would happen if you could peer inside the most extreme objects in our universe? Today we're embarking on a mind-bending journey to explore what lies above and below a black hole's event horizon, those cosmic monsters that bend reality itself into impossible shapes. What we're about to discover will fundamentally change how you see the cosmos, because black holes aren't just cosmic vacuum cleaners. They're reality-bending laboratories where the laws of physics completely break down, where time becomes a weapon, and where information itself might vanish forever. Just this year alone, we've witnessed discoveries that sound like science fiction. We detected black holes 225 times more massive than our sun spinning at impossible speeds, captured polarized images showing organized magnetic fields spiraling around our galaxy's central monster, and we're on the verge of creating the first actual movies of these cosmic beasts feeding in real time. If you're enjoying this cosmic journey already, go ahead and give it a like. It really helps the channel explore more mind-blowing space mysteries. But here's what will really blow your mind. The event horizon isn't what you think it is. It's not a physical surface you could touch or see. Instead, imagine standing at the edge of a cosmic waterfall where the water is actually space and time itself, flowing inward at the speed of light. Once you cross this invisible boundary, there's no swimming upstream. Even light, the fastest thing in the universe, can't escape the current. Einstein's equation tells us exactly where this point of no return forms, at a distance called the Schwarz Radius, where the escape velocity equals light speed. For a black hole with our sun's mass, this creates an event horizon only 6 kilometers across. You could walk across it in an hour if it wasn't, a black hole. But supermassive monsters like Sagittarius A-star at our galaxy's center, their event horizons span 16 million miles wide. You could fit Mercury's entire orbit inside with room to spare. Now here's where things get genuinely weird. Time itself becomes broken at the event horizon. If you were falling toward a black hole, from your perspective, you'd cross the boundary in just minutes, experiencing nothing special except empty space rushing past. But if I watched you fall from a safe distance, I'd see something completely different. You'd appear to slow down, freeze at the horizon, and gradually fade away as your image redshifts into invisibility. Both perspectives are equally correct. There's no universal referee to settle who's right, because time itself has different meanings in different places. Have you ever tried to imagine what it would look like above a black hole's event horizon? The region just outside hosts some of the most extreme physics in the universe. Accretion disks, those swirling clouds of doomed matter, heat up to millions of degrees through friction alone, glowing brighter than entire galaxies. The inner edge of these cosmic whirlpools moves at 42 million meters per second. That's 14% the speed of light, fast enough to circle Earth 1,000 times in a second. At exactly 1.5 times the event horizon radius, something incredible happens. This is the photon sphere, where light can actually orbit the black hole multiple times before either escaping or falling in. Imagine a cosmic racetrack where photons lap around the black hole like Formula One cars, creating those thin, bright rings visible in event horizon telescope images. When we first saw those rings in 2019, humanity was literally looking at light that had wrapped around a black hole multiple times. But the real fireworks happen with relativistic jets, streams of particles accelerated to 99.9% light speed that can extend for millions of light years. The longest jet ever discovered, called Porphyrion, stretches 23 million light years. That's like placing 140 Milky Way galaxies end to end. How does a black hole create something so impossibly huge? These jets are powered by the black hole's own rotation through a process so efficient it can extract 29% of the black hole's total mass energy, making it the most efficient energy conversion process we know of in the entire universe. Recent observations revealed something unexpected about the corona, that billion-degree cloud of particles hovering above the accretion disk. It acts like a cosmic particle accelerator, creating magnetic fields thousands of times stronger than Earth's that shape and focus these incredible jets. We're talking about magnetic fields so powerful they could rip the iron from your blood from millions of miles away if you somehow survived getting that close. But what about below the event horizon? What exists in that forbidden interior where our physics goes completely insane? The truth is, nobody knows for certain because our best theories completely break down. Einstein's equations predict something called a gravitational singularity, a point of infinite density where space-time curvature becomes infinite, and the laws of physics But most physicists believe this is mathematical nonsense rather than physical reality, like dividing by zero in a cosmic equation. String theory offers a wild alternative. Black holes might actually be fuzzballs. What's a fuzzball? Imagine the entire black hole as an incredibly dense tangle of vibrating strings with no true interior or singularity at all. The whole thing would be a single, extraordinarily complex quantum object storing all its information in string configurations, like cosmic DNA written in the fundamental fabric of reality itself. Loop quantum gravity suggests something equally mind-bending. If space-time itself has an atomic structure at the smallest scales, true singularities can't form. Instead, black holes might bounce into white holes that explosively release their contents. Could some of the mysterious gamma-ray bursts we detect actually be ancient black holes turning inside out? Would you risk everything to explore one of these cosmic monsters? For smaller black holes, tidal forces would stretch you like cosmic taffy in a process scientists charmingly call spaghettification. Your feet would experience significantly stronger gravity than your head, pulling you apart atom by atom long before reaching the event horizon. But for supermassive black holes, you could actually cross the horizon intact. Sagittarius A-star is so large that tidal forces remain manageable at its boundary. The visual journey would create the most spectacular light show in the universe. Starting 400 million miles away, roughly the distance from the Sun to Jupiter, your 3-hour journey would reveal incredible optical effects. The black hole acts as a gravitational lens, creating multiple images of background stars and forming Einstein rings, complete inverted views of the entire sky wrapped around the black hole's silhouette. But here's a crisis that keeps physicists awake at night. What happens to information that falls into a black hole? Quantum mechanics, one of our most successful theories, says information can never be destroyed. But black holes seem to permanently erase everything that falls into them. When Stephen Hawking calculated that black holes slowly evaporate through Hawking radiation, he realized this thermal radiation appears completely random, carrying no information about what originally fell in. Frustrated, this information paradox isn't just academic philosophy. If information can be destroyed, it would overthrow quantum mechanics and everything we've built on it, your smartphone, GPS, even the computer chips that make modern life possible all depend on quantum mechanics being correct. Recent breakthroughs suggest a mind-bending solution through something called the island protocol. Quantum entanglement might create islands inside black holes that are actually part of the external radiation, allowing information to escape, but in such a scrambled form that you'd need to collect more than half of all Hawking radiation to decode it. Remember how I mentioned time becomes a weapon near black holes? The time dilation effects are so extreme they essentially create cosmic time machines. At just 1.05 times the event horizon radius, 24 hours near the black hole equals 4.58 days on Earth. Get closer to 1.005 times the radius, and 24 hours stretches to 14.2 days. This isn't science fiction. GPS satellites must constantly correct for gravitational time dilation to maintain accuracy. Without these corrections, your navigation would be off by miles within hours. It's humbling to realize that someone falling into a black hole experiences completely normal time while watching the entire future history of the universe play out above them and fast forward. Both perspectives, the falling observer and the distant watcher, are equally valid. There's no cosmic referee to declare one correct because relativity means there's no universal time that everyone agrees on. Let me share some discoveries that sound impossible but are completely real. LIGO's gravitational wave detectors recently heard 2 black holes with masses of 100 and 140 times our Sun spinning at 80–90% of the maximum speed allowed by Einstein's relativity. That's 400,000 times faster than Earth's rotation. Astonished, when they merged, they briefly released more energy than all the stars in the observable universe combined, creating gravitational waves that rippled through the fabric of space-time itself. The Event Horizon Telescope didn't stop after giving us those first black hole photos. In 2024, polarized light images revealed organized magnetic fields spiraling from our galaxy's central black hole, showing that even these monsters follow cosmic rules. By next year, we're expecting the first black hole movies, actual footage showing how these giants feed and evolve over time. But James Webb Space Telescope discovered something that shouldn't exist according to our models. 70% of early galaxy candidates show signs of rapidly growing supermassive black holes when the universe was only 600 million years old. These little red dots contain black holes that equal 10 to 100% of their galaxy's stellar mass, compared to modern galaxies where black holes are typically only 0.1% of the stellar mass. How did they grow so impossibly fast? The telescope also found LED 568, a black hole feeding at 40 times the theoretical limit. This super Eddington feeding breaks our models of how quickly matter can fall into these cosmic monsters. It might explain how supermassive black holes reached billions of solar masses so quickly after the Big Bang. They simply ignored the cosmic speed limits we thought existed. Black holes come in dramatically different varieties, each telling a unique story about the universe. Stellar mass black holes form when stars over 20 to 25 times our sun's mass collapse after supernova explosions, creating monsters with event horizons the size of cities. The Milky Way alone hosts between 10 million and 1 billion of these stellar corpses, cosmic graveyards scattered throughout our galaxy. Supermassive black holes lurk at galaxy centers, ranging from 100,000 to 66 billion solar masses. The current record holder, 21618, contains 66 billion times our sun's mass. Its event horizon could engulf our entire solar system out to Neptune's orbit. But how did these giants form when the universe was so young? That's one of astronomy's biggest unsolved mysteries. The brightest object ever discovered, Quasar J0529-4351, contains a 17 to 19 billion solar mass black hole that consumes one entire sun every single day. It shines 500 trillion times brighter than our sun, a cosmic lighthouse visible from billions of light years away. Binary star systems have even been discovered orbiting Sagittarius A-star, something previously thought impossible due to the destructive tidal forces. What does all this mean for our understanding of reality itself? These discoveries remind us that the universe operates on principles far more exotic than our everyday experience suggests. Black holes aren't just objects in space, they're laboratories where the fundamental nature of reality gets tested to its absolute limits. Every new observation reveals that we're part of a cosmos more strange and wonderful than our ancestors could have imagined. The next generation of telescopes will revolutionize black hole science even further. The upgraded Event Horizon Telescope will create those movies showing black holes feeding in real time, while next-generation LIGO will detect gravitational waves from across cosmic history. We may be on the verge of discovering whether black holes are gateways to other universes, cosmic computers processing reality itself, or something even stranger than our wildest theories imagine. These cosmic monsters continue teaching us that our intuitions about space, time, and reality itself need constant revision. Every photograph, every gravitational wave detection, every unexpected discovery pushes us to think bigger and stranger about the universe we inhabit. That's the beauty of science. It shows us that reality is far more incredible than fiction could ever be. So here's my question for you. If you could safely observe a black hole up close, would you want to watch from outside as someone falls in, or would you be the one taking the plunge to see what lies beyond the event horizon? Share your thoughts in the comments below. I love reading your perspectives on these cosmic mysteries. Thanks for joining me on this mind-bending journey through the most extreme physics in the universe. If you want more explorations of space's deepest mysteries, hit that subscribe button, and I'll see you in the next cosmic adventure.